Right, good morning everyone. So I take it Krishna has been doing the dishes all night and using the days, but it's my pleasure to once again introduce James Maynard for his third talk on the primes and today's primes with restricted digits.
Okay, so thanks a lot. And if you guys are totally fed up with me, then this is my final talk. So you just have to put up with one more talk. Shut up. So today I'm going to talk about primes with restricted digits. So it's a slightly different topic to the other two topics that I talked about today, but it's the same subject. And the kind of thing I want to look at is let's consider the set of integers which have no sevens anywhere in their decimal expansion. So exactly the same argument is going to work with a 7 replaced by any other digit, but for the sake of argument, let's concentrate on the case of no sevens in their decimal expansion. And I'd like to study this slightly strange contour set of numbers. So it looks roughly like a Cantor set, and the basic question, since I'm interested in primes, is how many primes are there in this set A? Are there infinitely many primes, or are there finitely many primes? So I actually think this is quite a fun question just in and of itself, but maybe to some people in the audience it seems like a slightly odd or unnatural question. But other motivation as to why you might look at this, A is a pretty thin set of numbers, so it contains only about x to the 0.95 numbers less than equal to x. So the vast majority of numbers, when you're looking at big numbers with lots and lots of digits, have at least one seven. And so we're really looking at a very sparse set of numbers. And if you remember from my talk yesterday, I was saying that sparsity causes a big problem in lots of parametric arguments. There's various techniques that just seem to break down when you're looking at sparse sets, which have only x to the 1 minus epsilon elements less than equal to x. And often you need a certain amount of multiplicative structure to be able to get a good handle on such sets and be able to count primes and such sets. But this set A of integers with no sevens in their decimal expansion doesn't really have any natural multiplicative structure. It's not the case that if you multiply two numbers with no sevens in their decimal expansion, you get another number with no sevens in their decimal expansion. And so it doesn't really have the kind of multiplicative structure. So I'm presenting this, even if you don't care about numbers with no sevens in their decimal digits, as an interesting example of a sparse set of numbers that has no multiplicative structure, yet we're somehow still able to count primes in this set. And similarly, I guess, if you're interested in various mathematic analytical tools to count primes or arithmetic objects in certain sets, I claim that looking at numbers missing a digit in some base is actually a very useful first test case to see how well your tools can work, because there's certain nice properties of this set which means that you can get more explicit estimates than you might hope for in a general set. So this is like an easy test case where you don't have very explicit multiplicative structure, but you still have sparseness, but somehow in some technical ways it's slightly easier to get a handle. So anyway, whether you think this is motivated or not, this is the question I'm going to talk about. Well, let's first not worry about how we might prove anything and just think, let's have a guess at how many primes this should be. So let's look at numbers just with k digits, so up to 10 to the k. Okay, so choosing one number, k plus 1 digit. And we should think about whether primes are related to digits of numbers in base 10, or whether they're not related. And there's one obvious relation, that a prime has to end in 1, 3, 7, or 9, at least provided it's greater than 10. And this is a certain connection between primes and their digits, just because it can't be multiplied by 5. And if you think about it a bit more, it's quite difficult to come up with any other natural properties of prime numbers that is particularly related to their digits. So I guess there's things like the sum of the digits has to be cofactor 3. But the sum of the digits is somehow slightly different to the problem I'm considering here, although in many technical ways it's very similar. There's pretty fun work of modelling loop at. You look at the sums of digits of primes. So we scratch our heads a bit and we think that maybe it's the case that the last digit happens to be 1, 3, 7, 9 is the only really relevant property that the primes should have that are connected to their decimal digits. And so let's pretend that's true. Well, then if we just pick some uniform random integer n with k digits, subject to ending in 1, 3, or 9, then the probability it's in A is, well, there's k minus 1 remaining digits once we fix the last digits, and there's 9 choices of each of these digits if it's going to be an A, because you can't choose 7, but a general number, there's 10 different possible choices, so the probability that it's in our set A, since 1, 3, and 9 are not equal to 7, is 9 to k minus 1 over 10 to k minus 1. But similarly, the probability that n is prime if n is chosen with k digits and subject to ending in 1, 3, or 9.
Is there a reason why you made it 7 and 7 less?
Because A is numbers with no 7s in their decimal expansion. So this is a relative question, so I'm only going to be looking at primes that end in 1, 2, or 9 if they're going to be an n. So the probability that n is prime, if we take these things by Dirichlet's theorem on prime mathematical progressions, is 10 over the number of integers, k times 10, which is 4, divided by the log of the size of the prime finger. And if we thought that this was the only relevant property, then we might think that once we've taken into account this half digit, these two properties, being in A or being prime, should be roughly independent. So maybe the probability that it's a prime, which is in A, should just be the product of these two probabilities. So then we guess that the number of primes which are less than, which have k digits in A, is the probability that's in A, given that it has a suitable last digit, times the probability that it's primes, given that it's the last digit, times the number of integers n that we're looking at, which is 3 for the number of choices for the last digit, and then there's 10 choices for each of the remaining k minus 1 digits. And if you simplify that a bit, but for some reason don't cancel some factors in the numerator and denominator fractions, then you get that it's roughly, I guess, 5/6 of size of A. Oh, and there should be a log 10 to the k in the denominator here, which I forgot on this typo. So that's what we might guess as number of primes with k digits, such that there's no 7. And the main result that I want to talk about is that this is essentially correct. So our set A of numbers with no 7s in their decimal expansion does contain infinitely many primes, and moreover, we get a lower bound, which is essentially the right order of magnitude that the number of, if we're looking at primes which are less than equal to x, it's x to the 1 minus c, which is the number of elements in A, give or take a constant factor divided by log x, and this greater than sign just means I'm hiding a constant factor. So it's with x large enough, it's picking, say, 1 over 100 times x to the 1 minus c. And you get an upper bound, which is exactly the same thing, multiplied by a different absolute constant factor, fairly easily from sieve methods. And so this means that, give or take a multiplicative constant, you can count the number of times less than equal to x, which are in A. In particular, there's infinite many times, and then 7 in their decimal. I guess you might ask, well, I'm losing this multiplicative factor, so the number of elements of A which are less than equal to x is approximately x to the 1 minus c times a constant, but that constant oscillates with x. And so you can't expect an asymptotic formula of the form the number of primes which are less than x in A is equal to some absolute constant times x to the 1 minus c divided by log x. So you have to have a loss of multiplicative factor purely because the signs of A oscillate. However, we're still cheating a bit because our guess that we had beforehand, I would conjecture to be true, that it should be the case that you get this 38 over 36 times the number of elements in A, so you take into account the oscillations of A, but unfortunately I can't prove this, I still lose the multiplicative factor. And maybe at the end I'll mention why the techniques fail to prove an asymptotic form of this type here. But in terms of X, this is the sort of best kind of result. Help draw up to the precise value of these multiplicative constants. Okay. So how do we go about proving this result? So on a high level, the argument is going to be based on the Hardy-Edgewood circle method. So the Hardy-Edgewood circle method is a fairly general method, and it can be viewed as a method of counting solutions to equations, and in particular linear equations. So I want to view it as counting solutions to the equation p minus a equals 0, where p is a prime and a is an element of our strange set where we have no 7s in our decimal expansion. And the basic idea of the Hardy-Edgewood circle method is that you can further expand it. So normally it's written as an integral, but this is exactly the same thing as the discrete version of the Hardy-Edgewood circle method, using the discrete version form. So here I'm taking x to be our cutoff tending to k, and I'm thinking of x tending to infinity as k goes to larger and larger integers, and s sub p and s sub a are essentially just the discrete Fourier transforms of the primes and the discrete Fourier transforms of numbers with no 7s in their decimal expansion in the group z mod x. And E here is again the complex exponential equal to 2 pi r. So this is just essentially a Fourier exponential. I've rewritten this into our Fourier transform, and the idea is that we want to classify these frequencies A over x, which appear as a sum, and there'll be some A's which fall into the so-called major arc, with the main term contribution, and some A's which fall into minor arcs, which is an error term. Provided we can get an upper bound for the A's in the minor arcs and show that they're negligible, and we can get an asymptotic formula for the A's in the major arcs, we can get an asymptotic formula for this quantity, and hopefully this will be positive, and it will show that they're different in time. So, I'm slightly surprised I haven't been heckled yet, because it's a pretty well-known principle that this kind of argument shouldn't be possible, at least as I presented it here. That there's a well-known obstruction to the circle method of possibly proving solutions to binary equations where you just have two variables. And p minus a equals 0 is pretty emphatically a binary equation. And so this is precisely why we have difficulties proving the twin prime conjecture or Goldbach's conjecture, but we can prove the ternary Goldbach conjecture where we have one extra variable. And very roughly, if I choose some frequency a over x, which I think is beta, sort of just generically some random one, then you'd expect a certain amount of cancellation in these sums, but there's a basic principle that you shouldn't really be expecting better than square root cancellation generically. If these were just random numbers on the unit circle, you can't hope for sort of better distribution than just randomly two, as if they were randomly chosen, then both of these two Fourier transforms would be of size about x to the half. And so on the minor arcs, when you'd be hoping to just get an upper bound, morally you shouldn't really be expecting to do better than an upper bound size x to the half. But these typical features, there's x different summands, and therefore this means that our upper bound on the minor arcs would be an upper bound of size big O of x, which would swamp any main term that we're going to have. So it's bigger than our expected mean term by a full factor of full power of x. And so this, in general, is pretty hopeless. So one magical property of the Fourier transform of, okay, this is a typo. It's the Fourier transform of our set A of numbers with restricted digits, not the Fourier transform of times. If we won for this was true for times, but unfortunately it's not true for times. So this Fourier transform of numbers with restricted digits has some extra cancellation properties that actually mean for some typical theta, for suitable understanding of the word typical, it has better than square root cancellation. So this is one unusual feature of the set of numbers with digits, but the basic nice feature of the numbers with restricted digits is that it's a very confident Fourier transform that you can get very good estimates. And so one way to see this is that one lemma is that we get an L1 bound for the Fourier transform. So if we sum over all frequencies A less than equal to x, take the absolute value of the Fourier transform, well, it's certainly got to be of size at least A, and if we were guessing square root cancellation, you might guess that this sum is of size x to the 3 over 2, because there'll be some times when it's bigger, but maybe you'd hope x to the 3 over 2 in general. But in fact, we're only losing a factor of x to 0.35 rather than x to half. And it's, so in some sense, this is sort of saying, generically, our Fourier transforms may be of size more like x to 0.35 than x to half. And if we plug this in, if we had perfect square root cancellation of the Fourier transform of the times in the minor arcs, and we had this thing, maybe in some slightly stronger sense, typically being of size x to 0.35, then this means that minor arcs would be giving us a overall contribution of A times x to 0.85, 0.35 plus 0.5, divided by x, which is slightly smaller than A. So we at least have a small amount of room that means that we're not completely dead from the outset. Of course, this is based on various fairly strong assumptions, like having square root cancellation with Fourier transform of times, which is rather strong for me. But anyway, that's my brief justification as to why somehow I'm able to get around doing this thing that we morally know should be illegal and really shouldn't work at all. So, as you've seen on the previous slide, it's very important to try and understand this Fourier transform of numbers with restricted digits just on its own in some distributional sense to try and get a handle on this. And this is the key reason why these sets A are very nice indeed. So if we look at the Fourier transform of our set A evaluated with beta, then by definition this is just the sum over all elements of A which are less than equal to x, so this exponential. But I can then expand this A as its decimal expansion, and the property being A is just a property individually on each of the AIs. So after a little bit of thought, you realise that this factors as a product the sum of each of the sums is over the digits AI. And we know precisely what they range over. They just range over 0 up to 9, excluding 7. But then these inner sums here are just a geometric sum, so we can explicitly evaluate it. We know how to evaluate geometric sums, and we get this product expression for the Fourier transform of the function. And the key point here is that this Fourier transform depends only on the distance to the nearest integer of 10 to the, well, the ith term in this product depends only on the distance to the nearest integer of 10 to the I minus 1 times theta, where theta is our point here. And so then there's a nice trick that we can play. If theta itself we give as a decimal expansion, so it's some real number, but we can say it's 0. Blah, 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 and so on, then the distance to the nearest integer of 10 to the I minus 1 times theta, well, it doesn't depend at all on any of t1 up to ti minus 1, and then this is going to be ti over 10 plus ti plus 1 over 100 plus ti plus 2 over 1,000 and so on. And okay, this is a continuous function, so up to errors of say about 1 over 1,000, we could pretend that it only depends on ti and ti plus 1. So we can get a moderate approximation of this term in parentheses just in terms of the I and I plus 1 digits of theta expressed as a decimal. And so this means, at least up to some approximation, we have some approximate evaluation of our Fourier transform in terms of a product of functions which just depend on the two consecutive digits moving along. Okay, so why is that useful? Well, the point is that this expression here, once we've made this approximation, suddenly looks like a Markov process. that we're getting an extra probability, and we can think of it as a walk on the decimal digits of the decimal expansion of theta. So we can consider the Markov chain where we have random variables x1, x2, x3, x4, x5, taking values in 0 up to 9, so it's just 0 up to 9, with the Markov property that the values of xi plus 1 only depend on what value of xi is, and if xi is given by ti, then the probability that xi plus 1 is ti plus 1 is proportional to this constant, this function g. So this function g could be quite large, it could be as large as 9, I guess, and so you need to divide through to make sure these properties add up to something less than equal to 1, and provided they add up to something less than equal to 1, this is looking at a sort of sub-Markov structure, and we can then understand this by using techniques from Markov theory. And in particular, if we're summing over all paths in a Markov chain, and so this would be corresponding to summing over all possible decimal expansions of theta, and so in particular all thetas, we can understand moments over these sums based on the eigenvalues of the transition matrix of the Markov chain. And the key point here is that this is just a finite transition matrix, just a 10 by 10 matrix with these instances g of ti, g of tj, and the ij coordinate. And so this means that we can reduce estimating all moments of our Fourier transform in terms of just calculating eigenvalues of this finite matrix. So in particular, that MT being the 10 by 10 matrix where the ij entropy is g of ij raised to the tth power for whatever your favorite real number t is. And then if we want to estimate moments of our Fourier transform where we're looking at the tth moment, and here t can be any real, it doesn't have to be an integer, I guess it doesn't really have to be positive, then, well, we know that the Fourier transforms approximately given by this product of the GIs are, I guess, there's another typo here. This should be the G's that are raised to the tth power here. Summed over all possible paths t, because we're summing over all frequencies. But then this is just a sum over all terms in the kth power of our transition matrix.
T sub I has nothing to do with the exponent t, right?
Sorry?
T sub I has nothing to do with the exponent.
That's exactly right. Yeah, so this is maybe very bad notation. I apologize. So T sub I and T sub I plus 1 are just integers that range in set 0 up to 9. But somewhat confusingly, the exponent here that I'm looking at t is some fixed real number that has nothing to do with ti plus 1. I don't know why I chose t as the exponent. I'm feeling quite silly. But this is the sum over all entries in the k power of the matrix MT, and by the previous formula we know that this is an eigenspace of dimension 1, MT is irreducible, which it turns out it is, because we can assume all these g functions are always positive. And so this is up and bounded by the largest eigenvalue, some constant times the largest eigenvalue of this matrix MT raised to the kth power. And the key point here is that this is just a fairly explicit numerical calculation that we can do. It's a finite calculation, and this gives us an asymptotic upper bound for any moment we would possibly like for our Fourier transform. And, okay, there's this fudge because I've got this approximately equal to sign, and I'm actually losing a sort of full power of x essentially in this x approximately equals to sign, but I didn't need to approximate this Fourier transform just with ti and ti plus 1. I could have done it with ti plus 1, ti plus 2, or ti plus 1, ti plus 2, ti plus 3, and as I take into account more and more terms in this approximation, I get bigger and bigger transition matrices, slightly different values down to t, and these values down to t will converge to whatever the true constant here is that should be given the approximate right upper bound. And in particular, this means that if you only care about moments, give or take some very small loss in the power of x, then it just suffices to calculate the largest eigenvalue of a modular size matrix. So up to small errors, we therefore could get a good estimate for all moments of our Fourier transform set. And by the method of moments, this means that we essentially have, up to small errors, a good understanding of the entire distribution function of our Fourier transform. Okay, so we actually have this surprisingly nice explicit Fourier description of the Fourier transform of our set A, and we'd now like to use this Fourier description to try and go back and use our hard integral circle. So trying to estimate this something. Now, this is where maybe we're going to adopt a slightly different strategy to the standard circuit method. So standardly, you would split up into major arcs and minor arcs, and you get a bound for the minor arcs, and then asymptotic bound for the major arcs. And we're more going to do the same thing, but we're going to split the minor arcs into two further sets, sort of generic minor arcs, where it's sufficient to just use distributional information individually on our two separate terms, the Fourier transform of the primes and the Fourier transform of our set A, and this will show that for the vast majority of A's, there's only a small contribution, and we're then left with some exceptional set which will include the major arcs, and the major arcs will get an asymptotic formula, and then there's some small leftover set where we have to actually decorrelate these two functions. And morally, we should think of the Fourier transform of the primes being large when A over x is close to a rational small denominator, and the Fourier transform of our set A being large when A over x is close to a real decimal that has lots of strings of zeros or nines in its decimal expansion. And so because this is defined by digit conditions, and this is defined by Diophantine rational conditions, we expect the only time that you can have A over x simultaneously being close to a rational small denominator and having lots of zeros or nines in its decimal expansion to be the obvious case when A over x is close to a rational with denominator some small power of 10. Okay, so where was it? Okay, so let's first of all try and deal with the generic minor arcs, where we can just study distributional moments and the two Fourier transforms individually. So, as I mentioned before, we get this L1 bound, which means that in some sense the typical value of SA of theta is of size x to the power 0.35. So if we had if that was true in a slightly stronger sense, and we had maybe a pointwise bound for all features far away from rationals of the Fourier transform of the primes being bounded by x equal to 0.65, would be done. But unfortunately, even under GRH, we can't prove results which are as strong as this in a pointwise sense. So we're going to have to move to distributional information for the Fourier transform of the primes. And unlike the Fourier transform of our set A, we can only estimate the even moments, but we can estimate the second moment. So by particle, the Fourier transform of the primes all squared summed over A less than equal to x is just the number of primes less than equal to x. So depending on how I'm counting the primes, I'll take a quite factor, but that's of size about x. And this means that most of the time, our Fourier transform of the primes are maybe missing normalization. So I guess there should be a 1 over x here in my head, it should be an x squared. This means that most of the time it is the case that our Fourier transform of the primes does the square cancellation, although we have no control over where it particularly happens. So we can combine our L square bound for Fourier transform of the primes with an L 1.526 bound for our Fourier transform of our set A, and to say that most of the time the contribution in our circle method expansion is negligible. So outside of some small set of size x to the power 0.58, there's a negligible contribution. So you can restrict just to some much smaller set of possible frequencies. And this means that we dealt with the vast majority of those already. We can restrict to a small set, and so we're now left to deal with major arcs and the exceptional minor arcs, which are the sort of main contribution from this, the generic terms in this exceptional set. So the major arcs are the next easy to deal with. So as I said before, we expect the Fourier transform of the primes to be large when the argument is close to a rational small denominator, and we expect the Fourier transform of our set A to be large if there's long strings of zeros or nines in the decimal time. And we expect these to only coincide if the condition should only be the same if theta is close to a rational with denominators of small power 10. So by major arcs, I'll just take them to be the standard major arcs. So this is whenever we expect our Fourier transform of the primes to be large. We're just going to restrict our attention to when theta is very close to a rational small denominator. And because the Fourier transform of the primes is essentially some rational number, if we're evaluating an exponential, which is periodic modulo 1 at a point a over q times some integer, then what value it takes only depends on the value of that integer mod q. And so essentially, when theta is close to a rational small denominator, estimating these two Fourier transforms just boils down to estimating times in arithmetic progressions and that's a day in arithmetic progressions. And it turns out we now have to do both of these things using, I guess, the sequel graph theorem, and I think it's previous work, maybe of Cartesian Maynard, who got suitable distributional information about A and arithmetic progressions, at least for major arcs. And this means that we can get asymptotic formulae for both of these, and when theta is close to a rational small denominator, Fourier transform of the prime, which is roughly of size 1 over q, and the Fourier transform of our set A is essentially tiny unless q is to the power of 10. And so combining them together, we get precisely this case, we get an asymptotic formula for them, and this gives us our main term, which is precisely what we expected for the size of number of elements valued, but in 1 up to x times 30 over 36, divided by that missing log factor of this given. So then we kind of come to the hardest case, which is this exceptional minor arcs. So we're now thinking about frequencies that are constrained to some small set of size roughly x to 0.58, which don't lie in the major arcs, but otherwise we have essentially no control over this set whatsoever. And we'd like to show that somehow these frequencies make a negligible contribution. So in a very similar way to the Vinogradov principle that I said in my second lecture yesterday, by getting suitable bounds for exponential sums over primes, it suffices to get suitable bounds for certain bilinear sums associated with the problem. And once you work through the bilinear sums a bit, you end up with an expression like this. So if you've seen the standard an infinity bound for the exponential sum over primes, this is just a small generalization of this because we're trying to do it on average over A's in our exceptional set weighted by 3 or 9. And so what we really want to show is that this overall contribution is integral. So morally you should think of this inner double sum over A1 and A2 as saying the Fourier transform of the primes is large if somehow A1 and over x and A2 over x are diaphragm type. They're somehow related over the rationals. And then we want to say that, at least on average, if this inner double sum is large, then it can't be the case that these Fourier transforms are large. And, okay, this is a bilinear sum, and if n is trivial, then this double sum is almost as large as it can be all the time. And so this is a pretty impossible estimate to hope for, but if n is moderately large, say between x to the third and x to the half, then we might be able to show this, and if we can show this in this range, then we'll be done, or we can show that the exceptional minor arcs make a neutral contribution. So, if it's the case that this double sum is reasonably small, then we can just use the distribution information that we had before of on our Fourier transform of VAs and not really worry about the fact that it restricts to a small exceptional set, and this won't matter too much. The fact that the Fourier transform of times is contributing a small amount is on its own enough to say there's a small contribution. So, in particular, the right quantitative way of saying this is that if this double sum is smaller than n times x to the power 0.42, 0.42 is here 1 minus 0.58, size of our technical set, then that's good enough to use our previous distributional information to get this down to. So we then need to deal with the case when this double sum is bigger than n times x to the 1.4. So we might hope that generically this inner thing would be of size 1, and so for a totally generic A1 and A2, you might hope that the minimum always occurs at this thing, and this thing is always roughly of size about 1, and so this inner double sum is of size about n squared. And so we're not even in the typical case unless n is smaller than x to the whole 1 or 2, and so this is a necessary restriction for us to have. But if this is a necessary restriction, then this is saying that our double sum here is larger than we expect, and so there has to be some Dirac-Valentine relation between A1 over x and A2 over x. And it turns out that we can precisely prove this in a very explicit way. That if this sum is larger than we might expect, then one of the following two alternatives has to hold. Either A1 and A2 has to lie on the projection of a low height line. So in particular, this means that A1 and A2 satisfy the equation V1A1 plus V2A2 plus V3X plus V4 equals 0 for some VI's which are small, and so the height of this line L is given in terms of how much bigger than expected this double sum is. If it's not the case that they lie on a low height line L, then instead they must lie on the projection of a low height line lattice lambda, and if they lie on the projection of a low height lattice lambda, it means that they have a simultaneous rational approximation where we have rational approximations to A1 over x and A2 over x, which both have the same denominator. And so the key point here is that we started off with this double sum that was sort of morally saying maybe they should be Dirac-Valentine related, and we then got very explicit linear structure in the manner in which they should be Dirac-Valentine related. So this follows from the geometric numbers, so in many ways it's a similar idea to some of the things I talked about yesterday. So this is my even more embarrassing visual attempt to paint to try and do a 3D diagram as to the kind of geometric thing that's going on here. So I'm sorry that this is quite so expensive. I didn't have as much time as I'd like to do all things. So the point here is that instead of looking at distance to the nearest integer, we could just maybe put in an extra term minus integer n3 here, and it's more or less the same sum. And then we're looking at the dot product of the vector n1, n2, n3 with the vector a1 over x, a2 over x1. And so if this quantity then is going to be small, it means you have to lie very close to the line with axis proportional to a1 over x, a2 over x1. So in particular, you're living in some infinite cuboid where you're just a very small distance away from this axis here. So it's an infinite cuboid going around this line. And this is essentially some sort of count of the lattice points inside this cuboid. And, well, and if this double sum is unnaturally large, it means that you have more lattice points in this cuboid inside some bounded region than you would normally expect. And what would you normally expect? Well, we said before, it would always be sort of the volume divided by the lattice determinant. The lattice determinant here is just 1 because we're counting integer vectors, so it's just the volume of the cuboid that intersects a certain nice kind of cuboid. And so, if it is the case that you have unusually many, then essentially geometry of numbers will tell you that there has to be some lower height linear subspace on which many of these points are cuboids. And so there's only two possible types of linear subspace, which are a small subspace of our cubes, and that's either a line or a plane. And integer vectors in a line is precisely this condition, integer vectors in a plane is precisely what turns out to be this condition. So now we split the argument in two, we have to deal with the case when our frequencies are coming from one of these low height lines, or when the frequencies come from one of the low height lattices. And so for low height lines, we're just essentially looking at solutions to this linear equation. And here the key point is that we've restricted ourselves to some arbitrary but very small sets. And it turns out that we can say, regardless of what the set is, there can't be too many pairs A1 and A2 from this set that satisfy this low height equation. And so just based on the cardinality of the set, we can show that provided our bound to n is large enough, there's very few solutions to this equation, and in particular, this means that the bound that we have, we get a suitable bound for the overall set. So to control the contribution from the frequencies coming from sectional lines, based purely on the cardinality of the set. Now, you might be slightly surprised by that because I haven't used the fact that our exceptional set doesn't contain the matrix so far. We know that the matrix is the major contribution, and so it turns out that the key point where the matrix play a role is when these two frequencies, these two Fourier frequencies, lie on this low height plane, or junction of this low height plane, and so have this good simultaneous rational approximation. And so for low height lattices, we don't use the fact that we're in a small set at all, we just use the fact that we have this good simultaneous rational approximation, but then by large series-style attribution estimates, we can say that the Fourier transform of our set A restricted to numbers with which are close rationals somehow isn't some set where our Fourier transform accumulates, and so we get better than average. We get better distributional estimates for our Fourier transform A in these smaller sets by using variance of the large set. So, okay, so we wanted to decorrelate these two things. We turned it into a bilinear sum using bilinear sums of primes. We then reinterpreted this as a geometric problem. The geometric problem split into two. We dealt with low height lines. We dealt with where we were just using the fact that we were restricted to a very small set thanks to our previous distribution estimate. We dealt with low height lattices where we used the fact that we were outside of major arcs. And the upshot of all of this is that we can control the bilinear expressions that come up provided we have our parameter n in the range 0.36 to 0.42. So this is a pretty small range, and it turns out that if this range was a bit larger, then we'd be done. That it's well known from identities such as Vaughan's identity that we have enough bilinear sum information to get a suitable, to be able to express the Fourier transform of the primes in terms of bilinear sums controlled in these ranges. Unfortunately, this is too small, and this is where I only get a lower bound right order of magnitude rather than an upper bound. So we have to use a minus for the indicator function of the primes without the entire argument based on ideas on arm and sieve, and this gives us a lower bound for the number of primes in A. However, there's a problem. These arguments that give a lower bound don't necessarily give a positive lower bound. However, you can write this lower bound as are expected asymptotic times some sum of integrals which you can write down explicitly. And so then you have to use some numerical integration to estimate various four-dimensional integrals, and you find by just a whisker, this range is just big enough to make our lower bound positive, and so we do indeed get a lower bound of the correct order of magnitude. So this means that we can count primes in our set A, and there aren't any primes with no sevens in the set. So we just have to limp over the line, but that can be really good. Thanks a lot.
I think in view of the time, we leave questions for later, but please join me in thanking James for always being wonderful lectures.